Hello, everybody. This is Riley. I'm a STEM Center tutor for math and physics at the Brandon campus. And today I'm going to be going over some relevant material for your classes this semester, specifically the algebra sections that we offer at HCC. This PowerPoint that I'm going to go over with you is to show some of the solutions to problems which are about topics that your professors will want you to know coming into the class. So if at the end of this little presentation today you're still feeling nervous or unsure, please start a conversation with your professor to get more information and see what you can do, because your professors all want to help you succeed. So talking to them is going to benefit the both of you, and they're going to be able to help you with issues specific to your situation since they're going to be running your class. So I really encourage you all to talk with them, even if you're not having trouble, but especially if you are feeling worried or unsure. So with that out of the way, we're going to start going through this material to prepare you for your algebra sections. All right, so this problem is relevant to all of the algebra sections at HCC, and it's to do with operations on fractions, particularly adding and subtracting. So here we have a problem that is 1/2 minus 1/3. Now, with normal numbers, we can just conduct subtraction easily, and with fractions that have the same denominator, we can also do so, but these have different denominators. And a quick reminder, the top part of a fraction is called the numerator, so the ones here, and then the bottom is called the denominator. So the issue with this problem is we need to make sure that these have the same denominator so that we can actually conduct the subtraction across the top and get an answer. So here we've got to find something called the least common denominator so that we can have the lowest possible number that can be a denominator for both of these fractions. So in the case of two fractions with different denominators, we look for something that's we call it the LCD, and it's the least common multiple of the two denominators. What does that mean? Well, it's not the least common, doesn't mean rarest. It means the lowest value multiple that both denominators have in common. So we write out the multiples of each denominator. So we write the multiples of 2 and 3, and we find the smallest number that is a multiple of both. So here we see we have 6 as well as 12 is common to both of them as a multiple, but 6 is the lower one. So we choose this one in order to simplify the problem and continue with the subtraction. So the LCD here is 6. So we want to get both of these fractions with that denominator of 6. And so here's what we do. We take the fractions and we multiply them by 1. Now you might think, oh, I don't see a 1 here. Well, the 1 is just this portion highlighted in green. 3 divided by 3 is 1, and 2 divided by 2 is 1. And so we take the 1/2 fraction and multiply by 3 divided by 3, because that ends up giving us 6 here. And then we take the 1/3, multiply it by 2 over 2, because again, we'll get 6 as our denominator. And so we can now conduct the multiplication on the top and the bottom, and we get these two fractions. And now that they have the same denominator of 6, all we have to do is just do the subtraction with the numerators. So 3 minus 2, which gives us 1. And so our answer is 1/6. Another important topic for all of your courses, especially beyond college algebra and within college algebra, is dealing with operations, multiple complex operations in a equation or in an expression. So when we've got multiple different operations going on at once, we actually have a procedure for determining what we do first in order to get the correct answer. So this is called the order of operations. So here you can see we have exponents, minus signs, division, we have parentheses. So we need to know, where do we start? And so we have order of operations. We have an acronym for it. It's these yellow highlighted letters, and those tell you the order that we do these things. So first is parentheses. That means we look at anything going on within grouping symbols or parentheses, and we take care of that first. Then we take care of exponents right after that. Then when it gets to multiplying and dividing, even though the M comes before the D in this acronym, these actually have the same level of priority, or they're at the same level in the procedure. They both are equally equal in their position for performing them. So how we determine whether we do multiplying or dividing first is we read the expression from left to right, and whichever comes first is what we do. Same thing applies for addition and subtraction. So once we've completed all multiplying and dividing, then we go to addition or subtraction, and we follow those same rules. So for this problem, we start at the top with parentheses. We look and see if there's any parentheses that have things going on inside which need to be controlled, or which need to be evaluated. So here we've got -1 minus 4 inside the parentheses, so we take care of that. Now the parentheses are all done, check that off, and we look, see if we have any exponents, and we do, here and here. And so we take care of those, and we get 9 and 100. There's no more exponents, so we're done with that. Then we go to the next level, which is multiplying and dividing. So we read from left to right, and we determine which one to calculate first by which one appears first when reading it from left to right. So if we read this current line starting from the left, we see that the division comes first, so that's what we calculate beforehand, and we get 50. Oh, and a quick note, when we have a number next to a number inside of a grouping symbols, such as here, it's implied that we are multiplying those two numbers. So that's where this multiplication sign came from. So keep that in mind when you've got a complex problem, that you can rewrite this kind of expression as multiplication. All right, so now we check if we're done with multiplication and dividing, and we see that we still have multiplication to do, so we take care of that. And then lastly, we're done with that, so we do addition and subtraction, which means we just add those numbers, and this is what we get. So that's the correct answer for this problem. It's going to be key for your success in all your math courses, so make sure that you can handle it. All right, here, perform the indicated operation and simplify. So here, we're dealing with square roots, and those square roots, we've got some rules for dealing with them and simplifying them. And so first, we want to take a look at the whole question. We've got 7 square root of 2. We know that this can't be simplified because square root of 2 is square root of a prime number, so there's no way to simplify it. Same thing goes for 5. There's nothing that can be done. However, 18 is kind of a big number, so we want to see if we can maybe simplify it in some way with that square root. So first, we do something called prime factorization. So what that is, that means that we take a number and we factor it. In other words, we split it into things that multiply to give the original amount. And in this case, that factorization results in factors, which are the things that multiply to give you the original quantity. Those factors are prime. In other words, we keep splitting up the numbers until we are only left with prime numbers. So we take 18 and we see that it's even, so we can divide by 2 and we get left with 2 and 9. The 2 is a prime number, so we stop bothering with it. The 9, though, we know that it's divisible by 3, and we get 3 and 3. Okay, those are also prime. So now we found that 2, 3, and 3, multiplying those gives us 18. And so that's the prime factorization of 18. We factored it into prime numbers that are equal, when multiplied, are equal to 18. And so from the first line to the second line, that's what we've done, is replaced 18 with its prime factorization. Now we recall that for square roots are the inverse operation to the squaring of a number. So this 3 squared here gets undone by the square root, and therefore the 3 comes outside of the radical, and we get this. Okay, now we follow order of operations, so we carry out the multiplication, which gives us 12. Then we notice that we've got 7 square roots of 2, 12 square roots of 2, and so because we've got 7 of some number and then 12 of some number, that's the same as if we had a combined amount of that number. In other words, 7 plus 12 square roots of 2, which is 19 square roots of 2. At this point, we've only got square roots of prime numbers because 2 is prime and 5 is prime, and there's no more common terms to combine. So we're done with this example. We do have a radicals workshop on this topic, going over the mechanics of not only square roots but all kinds of radicals and the types of manipulations and calculations that you can do with those and that you might encounter in your courses, which is much more detailed. So please ask about that if you're interested. All right, another important topic, factoring. So just a moment ago, we did prime factorization, which is splitting up a number into factors. That is splitting it up into quantities that, when multiplied, give the original amount. Now, that was for an actual given number, like 18. Well, we can also factor equations or expressions that have variables or letters. So in this example, we do have y squared and y, and we also have some big numbers here that are in our expression. And there is a way to factor these kinds of things, and that's going to be an important tool for multiple different types of problems in your courses. So first thing that we do is we do the most generic factoring technique, which is we look for something called a greatest common factor. What that is, it's the largest number that divides all of a group of numbers. So in this case, we see we've got 16 as this coefficient, 72 as that coefficient, and then 40 as the constant at the end. We notice that they do have the trait that they're all divisible by 8. So their greatest common factor actually is 8, because there's no larger number that divides all 3 of these things. So what we do is we divide those numbers by 8, and so we get 2, 9, and -5 respectively, and we put the 8 on the outside of this parentheses, which, remember, that's the same as multiplying. So in other words, we haven't actually done anything to the value of this expression because we've divided everything by 8, but then multiplied by 8. So that is accounted for. Therefore, if you multiply out right now, you will get the original quantity that we had. Okay, now that we've done this, the numbers are a little bit smaller in this expression here, and it's more manageable for a technique that we're going to use. So this is called a quadratic expression because it's got a variable with a power of 2 in it. And so we have a technique for factoring these. So we first note some details, particularly the signs of each term. So we see that this here is a positive sign, this here is negative. We'll keep that in mind just for a moment, but we're going to proceed with the main starting point for this technique. So you might recall from the quadratic formula, or maybe you haven't got there yet, that's okay, but some vocabulary, I suppose. The first term, or the first coefficient, in other words, the coefficient that's multiplied with the highest power of the variable is called A, and then B is the next power, and then C is the constant term. So we've written A, B, and C here. The method we're going to talk about today is called the AC method. So what it is we take the product, then what we want to do is find all the ways that we can split -10 into two factors. In other words, two numbers that multiply to give -10, and we get this list here. Now this is where the details that we mentioned earlier come into play. First, we noted that the C was negative, so the two numbers that multiply give opposite signs. So that's, if you notice, that's why all of these 4 factorizations that I've written are, one of them is negative and one is positive. Then the B, this little plus sign, we've written their sum is positive. So what does that mean? That means that when we're looking at these groups of factors, the AC method tells us that we need to find the two factors which add to result in B. So in other words, +9. We want to find which group of these factors, when we add them together, we get +9. And so we've written that their sum is positive because that helps us eliminate some of these answers. Because this one, 1 and -10, that won't work since the negative number is larger, so their sum can't be positive. Same thing applies here. And then we can calculate and actually do the math and see that the one that works is this one, because we do get +9. So what do we do with that information? Now, since those two numbers add up to result in the same thing, since -1 and 10 add up to 9, we replace this little 9y here with 10y plus -y, because that results in the same quantity. Now that we've done this, we do the similar technique that we did at the start. We find the greatest common factor for this group and this group. And we notice that for the first one, it's 2y, and then for the second one, it's just a -1. There's an invisible 1 here. Okay, now that we've done that, we realize that for this whole expression, we have a greatest common factor of y -5. And so we factor that out. And what we're left with is the 2y and then the -1. And so that's how we do the AC method. So now that we've factored the quadratic expression over here into this, y +5, 2y -1, we can, we've completed the factoring and we've factored the original expression into the following. And so that's how you do the AC method for quadratic expressions. We also have a workshop for this topic where we go over all of the techniques that you might find applicable, and just all of the techniques that exist for factoring polynomials. In other words, for factoring expressions with a variable to different powers. Okay, here, more manipulation of fractions. So this time we're dealing with division, and we're also dealing with a variable in the mix, as well as some larger numbers than before. So, unlike addition and subtraction, we don't need a common denominator to conduct division or multiplication among fractions. All we need to do is it's much simpler. But first, we note that the numerators here both have a common factor that we can take out of the mix in order to have the problem slightly simplified. And so we notice that for the left fraction, we have 21 as the greatest common factor, and the right one, the numerator, has the greatest common factor of 7. So we take that out, and we notice we actually have the same expression here and here, x minus 1. Now, for dividing two fractions, the procedure for that is that we multiply by the reciprocal, in other words, the flipped over version of the divisor, which is the fraction that you are dividing by. So we take this same fraction and then we multiply, instead of dividing, by the flipped over version, which is called the reciprocal of the divisor. And so we have this. Now it's multiplying with fractions. And so multiplying with fractions, how it works is you multiply the numerator, and you multiply the denominator and the denominator. So we notice that when we do that, we have an x minus 1 that will cancel with this x minus 1, and then 11 will divide 110 into, to leave us with 10. The 21 gets divided by 7, and we're left with 3. And so at the end, we're left with 3 times 10, which is 30. And so that's how we get our final answer of 30 for this one. All right, here is a problem that unnecessarily stumps students. Solve this equation for L. So here's the exact pitfall. Students have a fear of the alphabet. So it's important to kind of overcome that fear. Lots of times students, what I mean by that they fear the alphabet is they're afraid of getting an answer that's not a number. They want numbers because that means that they can do something with it, and you know, a number is, it's better than a letter, well, according to them. So the point is, this equation, it's the same procedure as solving any other equation. All we want to do, if we want to solve this for L, we just want to get L by itself. Don't be afraid if you get something is equal to L that's not an actual number, but it's just an expression with letters. That's fine. Okay, so how do we get L alone? First, we divide by 2 on both sides because we see that L is being multiplied by 2. So we divide by 2 on both sides. Now L is getting W added to it, so we want to undo that as well. And so we subtract W on both sides, and there we go. Believe it or not, that's the answer. It's not a number, but it's okay. That's the correct answer. So please take away from this to not be afraid to apply the techniques you've learned for solving to get a number answer. Don't be afraid to apply them for other kinds of equations where you have multiple variables. It's the same procedure, same result. All right, solve the inequality. Write your answer with interval notation. So here, again, an inequality is nearly the same as solving an equation. The only difference is that we have to be cautious when dividing or multiplying by negative numbers, because that means that we need to flip the direction of this inequality sign. Aside from that, the main idea is the same. Just get R by itself on one side of this inequality sign. So what we do, first, we go ahead and carry out this multiplication because we need to get the r out of there. So we get this. Then, once we've done that, we can focus on the left side and try to get this r by itself. So we're going to add 14 on both sides. So it goes away here, and then we get -6 here. Now, we get rid of the 12r on this side so that the only r's are over on the left. And we did that by adding 12r. In general, you just do the opposite in order to make something go away. So since we had -12r, we add 12r on both sides. And so that's what we get here on the left side. Lastly, we just want the r, but it's being multiplied by -2. How do you undo multiplying by -2? You divide by -2. So we get goosebumps, our spider sense is tingling, and we remember that when we divide or multiply by negative numbers, we have to flip the sign of this inequality symbol. So when we divide by -2, we get this, but we've altered the direction of the sign because that's what you have to do when you divide or multiply by negative numbers in an inequality. Now that we've done this, this is our answer. That's correct. But you might be asked to write your answer differently, for example, graphing. So how can we do that? Well, for graphing, we just draw an arrow along a number line or a line segment to indicate the range of values that can give a correct answer. The catch is, for the points that mark our boundaries, we have to indicate whether those points are included as a solution or they're not. So if the endpoints aren't included, then on your number line, you will mark them with an empty circle. If they are included, you mark them with a filled-in circle, and you can imagine why. Similarly, we also have a different notation, which is called interval notation, and that is a written form of that same idea of a range of acceptable values that give a solution to an inequality. So in interval notation, we write the lower boundary and a comma, and then the upper boundary. And we use grouping symbols. Those grouping symbols that we use depend on whether the endpoints, so the starting and finishing point, are included as solutions. If they aren't included in your solution, we use parentheses for the point that is not included. If they are, then we use a bracket to indicate that it is included. So for our answer here, we just have r, we have that r must be greater than or equal to 3. So it can be equal to 3 or it can be anything bigger. So how do we write that in interval notation? It's as follows. 3 with a bracket because 3 is included because of this equals part here. And then it goes up to infinity. We can't include infinity because it doesn't exist, so we put a parentheses there. Find the slope of the line that passes through the points. So here we have 2 points where it's x, y, of xy form, and we want to find the slope of a line. If we connected these 2 points, what would the slope of that line be? So if we remind ourselves of slope, if we want slope of 2 points that are of this form, P1 and P2, where P1 has components x1 and y1, and P2 similarly, then we use the following formula. Slope is rise over run, which is change in y over change in x, which in terms of those points is this. So we first identify that in our case, we have P1 and P2 and its components, which are x1, y1, and then x2, y2. And we just clearly indicate to ourselves which ones represent the things that appear in our equation so that we don't get mixed up. And then we put them where they belong in that equation. And so if you do that, you will get this fraction here. When you conduct the subtraction, you get this. And then you notice, because you're very astute, that these have a common factor of 3. And so it's not simplified. This fraction is not simplified. So we take out the factor of 3 and we end up with this. Last, almost as important, or maybe more important for college algebra and beyond, is function notation. So functions are a rule, a mathematical rule, that you put in a number called an input and you get an output. So how do we denote that? We explain a function by writing the output or the input as some letter, usually x. That represents the number that you input. And then to define a function, what we do is we write this little thing here, f parentheses x. So what that is read as is f of x. What that means, the function, when you put x in, follows this rule on the right side of the equal sign. So this is an abstract representation of the function, and then this is specifically what rule that function is. So in this case, 1/2 of x and then -1. So it's not, this guy right here is not f times x, as we saw before with parentheses. It's f of x, and it means that we've got a rule where whatever is in this parentheses, we put it in the place of the x over here. So, for example, in part 1 here, we've got a 2 in the parentheses. That just means that we put a 2 where the x is. So you can see that I've just put a 2 here, and then you conduct the arithmetic, and you find your answer, that f of 2, in other words, the output when your input is 2, is equal to 0. But this doesn't just apply to actual numbers. It also applies to variable expressions, or expressions with letters. So here we have 4a. That's also fine. You do the same procedure as before. You just replace the x here with whatever's in the parentheses. So that looks like this. 1/2 of 4a minus 1, and we get 2a minus 1 is the output when 4a is the input. And then last, we have another example, f of w plus 4. A quick note, this is not the same as f of w plus f of 4. It's not the same. So don't make that mistake. It's the same as we had before. We just take this entire little phrase and put it where the x was. And so that looks like this. And we conduct that arithmetic, and we find our answer is 1/2 of w plus 1. And so that's how you deal with function notation. Lastly, another big topic in college algebra and beyond, intercepts, domain, and range of functions. So intercepts are just exactly like the name sounds. They represent when a graph of a function crosses or intercepts something. Specifically, we worry about y-intercepts and x-intercepts. So a y-intercept is where the function crosses the y-axis. In other words, since the y-axis is at the center of the coordinate system in terms of the values of x, since it's right at the center when you're looking at it from left to right, that means that it's right at the point where x equals 0. So there's actually a bit of hidden information there. We know that the y-intercept is when x equals 0. So therefore, we can just put x equals 0 into our function, and we will know what the output is at that point. Oh, and then a quick note, when we graph functions, we graph the output on the y-axis. So in other words, y equals f of x when we're graphing, and then x just equals x. So what do I mean? I just mean when we put in a point for x, our input goes with the x-axis, our output goes with the y-axis. So back to this problem. We know that the y-intercept occurs when x equals 0, so we put in 0 for x, and we find the output is equal to 3. Therefore, our y-intercept occurs at the point 0, 3. Similar idea goes for x-intercept. We know that at the x-intercept, that's when y equals 0. That's because the x-intercept occurs right at the midpoint of the graph of the coordinate system when you look at it up to down. So all we do is replace f of x with y, which is 0 at the x-intercept point. And so we have negative 5x plus 3 equals 0. We solve this for x, and we get the following coordinate. Another important topic is domain and range. So when we deal with functions, domain and range are important. What are they? Domain is the possible x values that you can, the possible input values for your function. So what can you have for x? And then the range is what can you have for y? So what can you get for your output? So domain, typically there's no restrictions on it. Only in 3 cases will you have restrictions. We cannot divide by 0. We cannot take square roots of negative numbers, and we cannot take logarithms of negative numbers. Aside from that, everything goes. So in this case, we can have whatever input we want since none of those things are occurring. Oh, and it's not just square roots, it's any even powered roots. You can't have negative numbers. You can't find the even powered root of any negative number. So in this case, the domain is whatever we want. Then for the range, that will depend on the domain. So we know that we can have whatever x we want. So that means since our equation up here is a line with a slope of negative 5, it will look something like this, and it will keep going like that because we can have whatever x we want. So we see from this primitive sketch here that we can have also as high of a y value as we want and as low as we want. In other words, we can have any number for y as well. So the answers for the domain and range is negative infinity to infinity for both of those. Okay, well, that's been the Smart Start workshop. Hopefully this taught you something or made you feel more comfortable for your upcoming algebra classes at HCC. Also, come and check us out at our tutoring at the STEM Center, BLRC 200, above the library at the Brandon campus. We also have online tutoring available by appointment at our website, where the link is written right there. Thanks.